Welcome to my YouTube channel. This is actually the first video on this channel, so I want you to please subscribe, like, comment, share, and turn on your notification button because you're going to be loving the videos that are gonna be dropping on this channel. So this channel, since this is the first video, I'm gonna be just introducing the channel. So this channel we basically been doing physics, exploring physics, and I'm going to be starting from the very basic of physics, and that has to be the high school physics. Then I go a little advanced into the college physics. So please don't mind my handwriting, but I will try as much as possible to make it clear for everyone to see, right? So we will be using three textbooks basically. We'll be using New School Physics. I actually love this textbook well because it is easier to understand. We have Lamlat Physics. This textbook provides a lot of questions, a lot of problems we can solve, and also college physics, which is a little bit advanced. So these two textbooks is more of high school basic physics, high school physics, secondary school physics. Then this is a little advanced, which is about undergraduate physics, undergraduate or college physics. So today, what are we doing? We will be doing unit and dimension. But just before that, I would like to, just give a little definition of what physics is. So physics is the study of matter and the relationship of matter and energy in our society or in our world. Let me put it that way, or in the science world. So we try as much as possible to understand how things relate or behave or act the way they do in relation to energy. Yeah, that's what physics is all about. So today I'm going to be talking about unit and dimension. And so this is basically about measurements in physics. And just like everything literally has a name, same thing goes for physics too. Everything has a measurement because there's no scientist that wants to give a data that wouldn't, give those data a name or probably a dimension or probably a unit or a measurement. So this is the basics of physics. So we have fundamental units or fundamental measurement, and we have derived units, or we can say derived measurement. So what is measurement basically? So measurement is very important in the aspect of physics because no matter the experiments you do, you have to give a measurement, you have to give a data. So measurement is basically a means of communication between scientists. So for example, let me give a very literal example because this channel is meant to, meant to explain every concept in details, and is meant for everyone, not just for scientists. So for example, if you are going to a store to get some clothes, now we have clothes 1. Let's assume clothes 1 is experiment 1. So clothes 1 has a label or a size which is small, Then cloth 2 has a label which is, let's say, extra small, I think. Yeah. Then we have cloth 3, which can stand for experiment 3, stands for big. Now if you look at this experiment 1, this experiment 2, this experiment 3, if I want to explain or give a comprehensive explanation of this cloth now, I can say cloth 1 has a small size, cloth 2 has extra small size, cloth 3 has a big size. So this is the basic the basic explanation of what we are going to do today, of measurement, unit and dimension and measurement. So for example, let's talk about, so we have two types or two basics of measurements, or let me say dimensions or units. Let me just use those three words. So I can use those words interchangeably. So bear with me. So we have fundamental, then we have the derived. Now we can say fundamental quantities, sorry. So we can say fundamental quantities, we can say unit, and we can say dimension. Same goes for derived quantities, derived unit, and derived dimension. Alright, now what are fundamental quantities? Fundamental quantities are basic, just like the English word fundamental. They are basic quantities that are independent of other quantities. That is, they are independent of other quantities. They cannot be defined in terms of other quantities. While derived quantities depends on fundamental quantities. Derived quantities depends on fundamental quantities. Now I'm going to draw something like this. Give me. I'm trying to erase this. Okay, so I'm going to draw a tabular form just to show the difference between these two. We have fundamental and we have derived. Now in fundamental quantities, we have three basic quantities, three all over the world, accepted all over the world. Now, especially in physics, so we have three. We have length, so this is a quantity. Then we have mass, then we have time. Now the unit for this is centimeter. We can also have meter, we can have millimeter, we can have inches, then we have kilogram, we have gram, we have pounds, and so on. Then we have seconds, we have minutes, and we have hours. Now derived quantities. Now I said derived quantities are quantities gotten from fundamental quantities. Now derived quantities, we have a lot of examples. We have area, we have volume, we have density, we have velocity. We have a lot of quantities in physics actually, so we can keep on listing and listing. Acceleration, we have force. As we go on in exploring physics, I'm going to explain what is area, density, acceleration, force, energy, and some other quantities which I might mention in this video. So we have energy, we have force, we have pressure, we have momentum, we have electric potentials, we have electric force, we have gravitational force, we have a lot. We have electric resistance, we have capacitance. So these are derived quantities. Now, all these quantities are gotten from just these three basic quantities or three fundamental quantities. Now, let us see how these quantities, these derived quantities, are gotten from fundamental quantities. So that will lead us to dimensions. Dimensions. So let me clean this off. Sorry. Let me just do this to make it faster. Yeah, so that will lead us to dimension. Dimension, how we can actually derive fundamental units. So derive how we can actually get derived quantities or derived units from fundamental units. Now, for example, I'll start from the basic one. Let's list some here. Area, volume, density, velocity, acceleration. I'm going to do as much as I can do in this video. So this will just, give you a basic understanding on how all these quantities in physics come about, how we derive them, why we use them, and why they are used for this purpose. So we have power, we have pressure. Should I stop here? Let me add one more. Momentum. Yeah. Okay. So let's start from area. Now remember, our fundamental unit is length, which is L, mass, which is M, LM, and we have time, which we can represent as T, and these as meters, and this is kilogram, and this is seconds. So that's it. So we measure length in meters, we measure mass in kilogram, and we measure time in seconds. So now, for example, area, we all know area is length times length, right? Length times length. So this will be L square. So we call this the dimension. We call this the dimension. Now, in terms of units, now we know area to be length multiplied by another length. So the unit of length is meters, right? So that would be meters multiplied by meters. So that's why we have the unit of area to be meter square. Hope this is understood. Let's move to volume. I'm going to rub this off. Let's move to volume. Yeah, volume. Now, we all know volume to be length times length times length. Yeah, right? Now, in dimension, this is 1, 2, 3. So this is L cube. Now, in units, the unit of length is meter. So we have 3 m's. So multiply both the 3's together. So we have m raised to power 3. So this is the dimension for volume, and this is the unit for volume. So that's why when you see an expression like 3 meter cube, 3 or 5 meter cube. So when you see this expression, know they are talking about volume. And also when you see an expression which is 3 meters square, know they are talking about area. And when you see an expression that they write just 3 meters, know they are talking about length. So that's, you can see, this is the basic fundamental. Now from the fundamental we got area, and from the fundamental, we also also got our volume. So that's the relationship between derived quantities and fundamental quantities. These are fundamental quantities and these are derived quantities. Now we have been able to solve these two. Now let's move to this, to density, velocity, which are more complex but actually, easy to understand. So let me rub these off. Right? So let's move to density. Now, what's the formula? So it is very important you know the formulas for this. Like area, I said length times length. This is length times length times length. So what's the formula for density? Density is mass. Density is mass over volume. Now, our mass is here, right? Which is the fundamental. Remember our volume, we calculated it. So mass is m. So I'm trying to get the dimension now. M. Volume is what? Length times length times length. Now we have m all over L raised to power 3. Now remember from mathematics, when you have 1 over L3, we can also write it as L raised to power minus 3. So this can be written as ml raised to power minus 3. So this is the dimension of density. Now let's talk about the formula for density, or the unit, the unit for density. Now density is mass, which is kilogram. We divide it by volume, which is meter cube. So this will be kg all over meter cube. So we've gotten the dimension and we've gotten the unit. Now let's move to velocity. Let me try and rub this off again. Yeah. Yes. So let me move to velocity. Formula for velocity is distance over time. So getting the dimension for this, for velocity, we all know distance to be also the same thing as length. So we can say length over time. We can also, distance and length are the same thing. They are both measured in meters. So we can say L over T. L over T. So this is from mass again. You all know that this can be written as L multiplied by 1 over T. Now, 1 over T can be written as T raised to power minus 1. So that's our dimension for velocity. Now, how do we get the unit for our velocity? How do we get the unit? Now, length is meters. So we have meters divided by time, which is seconds. These are the fundamentals. So we have meter per seconds. So that's why our velocity is described as what? Meter per second. So this is unit, this is dimension. Okay, let me solve for others like acceleration, force and all. Let me see if I can finish everything. All right, I hope you guys are getting what I'm doing. So let's solve for acceleration. Now acceleration, formula for acceleration is velocity over time. So remember velocity, so let's do this one by one after the other. So let's do for velocity first. So getting the dimension for velocity. Velocity is distance over time. That's L over T divided by, this division is here, by time, by T. Now, velocity, which is distance over time, L over T, you can write that again. Then you change this, mathematics principle. When you change this to multiplication, this becomes 1 over T. So we have L over T square. Now this can be written as LT raised to power minus 2. Now this is the dimension for acceleration. Now let's try and get the unit for acceleration, which is quite easy. So let's get the unit for acceleration. The unit for acceleration. Now, velocity, remember velocity is what? Distance over time. Distance over time. You can write L or D, anyone you prefer. Distance over time divided by this time. Now, what is the unit? I wrote them here. So the unit of distance or L, which is M, time, seconds, which is S, then divided by seconds, which is, divided by time, S. So we can do this like M over S. When you change this to multiplication, it's become 1 over S. So we have M all over S square, because M times 1 is M, S times N is S square. So this becomes MS raised to power minus 2. So you can see that this is the unit of acceleration. So we got the unit of acceleration to be ms minus 2 and the dimension to be LT minus 2. So this dimension and this unit. Hope you get that. Alright, so let's do force. Let's do force. So the important thing here is that you have to know the formulas for these derived quantities, because these are basically derived. We have a lot, so these are the ones I mentioned, but these are the fundamental. These ones are fundamental units. So we basically use these three to derive this. So that's the relationship between fundamental unit and derived unit. So I'm going to continue to derive. So let's derive energy. We all know energy is the ability to do work, right? That's just a very simple definition. So we have force times distance. So energy is force times distance, the force you applied, and the distance covers. Just imagine you carrying a load. You carry the load. Let's say this is a load from point A, and you carry that load to point B. Now you started your journey all the way from here, and you ended your journey here. So what has happened between here and here? You have applied the force, and you've covered the distance. Now you cover the distance. So that's what energy is. It's the ability to, work, ability to do something. So let me derive the unit first, or let's do dimension first. So dimension, force. Now we have force times distance. Dimension, what's force? Force is mass times acceleration. Now multiply by distance. So if you want to calculate this, especially for high school students, you have to do it one after the other. You don't rush, so that you don't mess things up. So now force gave us mass times acceleration, and we still have our distance here. Now we are trying to get dimension. Now remember I said mass is written as m, right? Now acceleration is velocity over time. You can see how I am breaking these things down. Then we still have our distance. written. Now let's break it down again. We are trying to break it down into the basic units, that is the fundamental units. Now we have our mass written down, then velocity. Now velocity is what's distance over time. So if I write that, that's distance all over time. So I have two times under here. Velocity is what distance over time with this t, which is here, multiplied by d again. So if I do this, this will be m times distance. I told you you can represent it with L. So L all over t square multiplied by L. Distance L, exactly. So now we have m L square over t square. Now you can rewrite these as you can write this as ml square t raised to power minus 2. It's as simple. So you can see all the way down, breaking it down. So when I broke it down into the three fundamental quantities, which is mass, length, and time. So you can see I got my dimension. So if you want to get the unit for energy, which is quite easy, so let's try and get the unit. So let's try and get the unit for my energy. Now we know force is Newton, measured in Newton, and distance is measured in meters. So unit is what? Just Newton meter. Or since force is mass multiplied by acceleration, mass is kilogram multiplied by acceleration is meter per second square. Then distance is m. So you can write this as kg meter square s raised to power minus 2. Simple. So this is unit and this is dimension for energy. So I think I'm just gonna stop here. You can try and solve power. Formula for power is force times distance over time. Let me clean this so that you can see it clearly. Alright, so formula for power is force times distance over time. So if you follow the other examples I did, you should be able to do this. Formula for pressure is force over area, and momentum is mass times velocity. So you should be able to solve this easily just following the examples I did. Right? Okay, so we are getting to the end of the video.